All right. Well, somebody told me that you could find a solution for any of the AP physics problems by searching YouTube, and turns out that this one that we either did on a test or did in class, it's like got one video that's in really bad shape. So I thought it'd be worth talking about. And this is a really good problem from a kind of a dark time in the AP test. So this problem has some mistakes about it or some ambiguity about it that we may need to satisfy. So we got ourselves in one of these situations where we have a mass on a spring, but there's another smaller mass sitting on top of it. And the smaller mass is lowercase m1 and the big mass is uppercase M2. And they say a small mass it rests on but not attached to a large mass. It slides on its base without friction. So there's no friction here at the bottom. A maximum frictional force between M1 and M2 is F. So that's the maximum frictional force. That's going to be a static force, and it's the maximum amount. Could be less than that. A spring of spring constant K is attached to the large mass and to the wall as shown above. What they don't say here, and that they usually say, is you give your answers in terms of this, that, and the other thing. So I want to caution you not to add complexity to this problem. One thing we should do before we get started is to go ahead and draw a free body diagram for these guys. So the easier free body diagram is probably the free body diagram for the mass on top. And I'm not going to draw the vertical forces, just the horizontal forces. So if this thing is pulled to the side and moves back, then there needs to be a force on M1 to drag it along with M2. And that is going to be a frictional force whose value is F, but at the maximum is this F that's listed here. You can see why they've created this ambiguity. Now, the other mass, mass 2, has two forces on it. One is there's a spring pulling it to the left, and that will be a kx value of the force. But there's a reaction from the frictional force going the other way. So there is a bit of a battle here on mass 2. Okay, now we read what they want us to do. They say determine the maximum horizontal acceleration that M2 may have without causing M1 to slip. So we want no slip, and no slip means that the acceleration of mass 2 is going to be the same as the acceleration of mass 1. So in order to determine the acceleration of mass 2, it's probably easier just to find the acceleration of mass 1 because it's only got one force on it. The acceleration of mass 1, well, the mass of 1 times the acceleration of 1 will be at most this frictional force. Therefore, the acceleration of mass 1 equals this frictional force over m1, and that will also be equal to the acceleration of 2. So the acceleration of 2 that is the most before slipping happens is this much, and strangely enough, it is governed by the mass of mass 1. Now they say determine the maximum amplitude A for a simple harmonic motion of the two masses if they are to move together, i.e. m1 must not slip on m2. So we already know that the maximum acceleration is going to be this value. I'll write it down again, although this is kind of ridiculous because it's just above. And we need to figure out how far you can pull this thing to the side. What is the amplitude of the motion? And one of the ways to do this, and probably the fastest way to do it, is just to remember that in simple harmonic motion, the maximum acceleration, which occurs at either end of the motion, is a times omega squared. And for the mass and spring system, omega is square root of k over m. So that needs to be squared. That just gets rid of the square root. But the big question is, what m is this? And the answer is that it's actually the sum of the masses. It's the total moving mass. Because if M1 does not slip on top of M2, they're going to both be in simple harmonic motion going back and forth. So that means that this maximum acceleration, which will be F over M1, must be equal to A, K over, and then the quantity M1 plus M2. And through the power of algebra, we can figure out that A has to be M1 plus M2 over M1. So there's a ratio of masses, and then F is on top and K moves to the bottom. This is the maximum amplitude that you can pull this thing to the side before M1 slips. Now they ask us something slightly different. They say the two mass combination is pulled to the right, that maximum amplitude, and released. Describe the frictional force on the small mass during the first half cycle of oscillation. So we're going to have this device up here is going to be pulled to the side, and it's going to accelerate back towards the equilibrium position and then compress the spring and stop here. And that's the first half cycle of the motion. So it's pretty clear that the frictional force on the little mass is going to be this way, and then it will drop to 0. And then when the little mass gets in here, the frictional force will be this way. So we have a negative directed force that goes to 0 and goes that way. And of course, the force will be sinusoidal. So this right here is the halfway time. Actually, this should be period divided by 2 on this graph. And this here is minus that F max. Now, there must have been some sort of issue with the scoring of this exam, because when you look at the grading rubric, they say that on this section here, that they're going to grant full points for any discussion that it's a sinusoidal force. So you could have even gotten it backwards or done something else, but you needed to mention that it was sinusoidal. I think that means that what happened is that people had all kinds of essays written and they were just looking through vast amounts of text. If I had to write this as an essay, I would say, this little conceptual drawing, I'd say it in words. I did it before on this one here. I said to the right is positive, so force is negative. The max force acceleration is at either end, so we start with minus F and go to 0 at equilibrium and up to positive F at the other extreme. So that's one way you could say it. Now we get on to the second half of the problem, and then you got the AP wrinkle. That's where they like to change something about the problem. And it says the two mass combination is now pulled to the right a distance A prime greater than A. So I think what they're saying is that A prime is greater than A. I don't think that they're saying that the distance, the new amplitude is A prime plus A, but you could read it that way. So I'm not going to do this. I'm going to do this. Now, if you pull it out a distance A prime, which is greater than A, that means that when M2 shoots back, it's going to be going with too much acceleration, and M1 is going to slip off. But they don't give us any information about the kinetic friction. They just give us the maximum static friction as the letter F. But luckily they ask for the instant the masses are released. So I think what we're talking about is that the instant the masses are released, you're going to have this situation. That the force on the little mass is going to be at its maximum, F, and that the force on the lower mass is going to be larger. It's going to produce an acceleration that is larger than the acceleration produced by this. And so that's when the slipping is going to begin. I think that's the best way to interpret this. Again, it's not really well worded. I think they had trouble this year with this question. So the acceleration of mass 1 when they're released is just going to be its maximum value, which it was before. And the point is that this just is going to be less than the acceleration of mass 2. They're no longer equal. They're going to be slipping relative to each other. And now the acceleration of mass 2 is going to be easy to find. We have a free body diagram up here. And so what we're going to do is we're going to say that the positive force, which is the F, minus the negative force, which is K times A prime, and this is all going to be acting on, if we divide by the mass, and in this case it's just M2, because it's now has a different acceleration. That's going to be equal to the acceleration of mass 2. What I did is I did net force equals M times A. I just wrote this as F net divided by M. I do so much of this that this is in my head right now. Okay, that's the solution to this thing. I have to go deal with whoever's pounding on my door.